Welcome to my channel of Physics Infinity. I am going to take on yet another problem on electrostatics, where I am going to talk about the charged conducting spheres, and when these spheres are connected to each other, then what happens, how do the charges get distributed. I have already done lectures on charged spheres earlier, but this one is going to be a unique case where finally I am going to take the case of a three concentric spheres XYZ, radii R1, R2, R3, and then I charge them initially, and then I connect the inner sphere, that innermost sphere X, to the sphere Z through a hole in the sphere Y, and then see how do the charges get distributed. Like in my earlier videos, I've explained to you that in the case of such problems, the major thing is the charge distribution. Once you are able to do properly the charge distribution, then all other problems can be easily handled, like potential at a certain point, the difference of potential between the two spheres, intensity at a particular point, energy of the system, and so on. Well, that is all subsidiary items. First and the foremost thing is, how do the charges get distributed? So in this video, I am going to concentrate only on this particular aspect. I have actually given you three situations on the board. In the case A, I take it as a case studies, case A, case B, case C. In the case A, let's take one by one. In the case A, I have got two concentric charge spheres, okay, radii R1 and R2. The inner is the plate X and the outer is the plate Y. Concentric spheres, metal concentric hollow spheres, thin metal hollow spheres. The inner sphere, I give it a free charge Q1 circle. Well, that's what I have been always teaching. Q1 circle is the free charge given. Q2 circle is the free charge given. Then how do the charges get distributed, and what happens when I change certain constraints? So right now there is a switch between the plate X and the plate Y, and the switch S is open. That means the two spheres are not connected to each other. Then of course Q1 will spread evenly on the outer surface of X, Q2 will spread evenly on the outer surface of the sphere or plate Y. Fine, nothing to discuss in that. We have already discussed details of that in my earlier problems, or in my earlier videos on problems on concentric charge spheres. Now what I'm going to do is, I'm going to close the switch. When I close the switch, that is S, then technically both the conducting plates become one plate. When I talk of plate, remember in electrostatics, every body, conducting body, we call a plate. So even a sphere I am going to call a plate. So the two plates are now at the same potential. They are in fact one body. So what will happen? The entire charge Q1 will transfer and reside on the outer face Y2 of the plate Y. Easy? Then this is a system where a sphere of radius R2 has a charge Q1 plus Q2 spread on its surface. So this is how the charges get distributed. Now I want to know what is the electric field, I want to know what is the potential, I want to know what is the electrostatic potential energy in the field of system. Well, that's subsidiary matter. Such things we have already discussed. So important thing we learn, that when the switch S is closed, all the charge Q1 on the plate X will transfer on to the plate Y. Over. This is over regarding the charge distribution in the case of case A. Let me go to case B. In the case B, I have got two metal balls. Well, they may be hollow, they may be solid, that doesn't matter. Plate X, plate Y, radius R1, radius R2. Then once again, I give free charge to Q1 to plate X, Q2 to Y, and the two spheres I connect them via a switch S. Of course, I am using a conducting wire for that. Switch right now is open. So no issue. Q1 is on plate X, Q2 is on plate Y, and whatever I want to ask, well, what is the capacitance of the system, what is the energy of the system, what is the potential difference of the system, that can easily be done. I have already done that in one of my earlier videos. You can refer to my video library. Now what will happen when I close the switch S? When I close the switch S, then what is going to happen? The total charge Q1 and Q2 will be now shared by the system, by the two spheres. And they will be shared in such a manner that the PD of both of them is same, because both the spheres after connection becomes one conducting body. So the potential should be same. So either you can solve, and now of course my purpose is, what is the charge? What will be now the charge on each sphere? Because once we have done that, then the other problems can follow. Right now in this video, I am only concentrating on the charge distribution. So here you are. When the switch is closed, so either you can solve this problem of the charge distribution on each plate by taking the potential to be the same, or the other way is, why don't you use the knowledge of capacitance? You all know this is a sphere of capacitance 4 pi epsilon naught R1. This is a sphere, okay, it's a larger metal sphere of radius R2, so its capacitance C2 is 4 pi epsilon naught R2. Then the total charge is Q1 plus Q2, which will be shared according to their capacities, So in that case, in the case of case B, I can take, while I am talking of the case B, I can take, well, charge on the plate X to be C1 upon C1 plus C2, because C1 plus C2 into Q1 plus Q2, where C1 is 4 pi epsilon naught R1 and C2 is 4 pi epsilon naught R2. Similarly, charge on Y will be C2 upon C1 plus C2 into Q1, total charge Q1 plus Q2. Well, you solve the problem. So this is the case B. Now I will move on to the case C. Now this is interesting, a little tough and more interesting problem. The main utility of this particular video is actually the case C. In the case C, I've got three concentric spheres, X, Y and Z, common center. So radii R1, R2 and R3. Now what I do, I have a switch S that is between the plate X and the plate Z through a wire, and the switch is connected by a wire which passes through a hole in the plate Y, in the middle plate. Right now the switch is open. So Q1 is on the plate X, Q2 is on the plate Y and Q3 is on the plate Z. I can easily do that charge distribution. If I take the faces X1, X2, Y1, I can take this one, let's say X1, this is X2, this is Y1, this is Y2, this is Z1 and this is Z2. So when the switch is open, we have done this problem earlier. Anyway, I repeat it for you. Well, on the face X1, the charge is 0. On the face X2, the charge is Q1, floating plate, charge conservation. On the face Y1, according to Gauss's law, the charge should be minus Q1. On the plate Y2, on the face Y2, the charge should be Q2 plus Q1, because the total charge on the plate Y is Q2. Fine. Then floating plate charge conservation. Then on the face Z1, according to Gauss's law, it will be the negative of the charge on the face y2. So it will be negative of q1 plus q2, negative of q1 plus q2, and then on the face z2, it will be the charge q3 plus q1 plus q2. Let me show you the charge distribution now. 0 on x1, on the face x1, q1 on x2, charge conservation, floating plate. Oh, okay, charge conservation. Right now I am talking when the S is open. So floating plate, all the three are floating plates. Minus q1 on the face y1 according to Gauss's law. q2 plus q1 on the face y2, floating plate, charge conservation. Gauss's law will tell us that on the face z1 it will be minus of this, so minus of q2 plus q1, and on the face z2 of the plate z it will be q3 plus sum of this, so q3 plus q2 plus q1. This is the charge distribution when all the three plates are floating, the switch S is open. Right. Now I close the switch. The interesting thing starts. The real game starts. I close the switch S. I close the switch S. This means the plate X is connected to the plate Z. Now normally in the situation 1, many students would think that all the charge Q1 will fly over and go to Z. No, not in this scene, because in between there is a plate Y which is charged, and this will not allow the total transfer of the charge Q1 from the plate X to the plate Z. So what to do? Let us assume a part of the charge goes and what remains is Q1 dash. Okay, let us assume that let the charge remaining on X be Q1 dash, and the remaining charge, that is Q1 minus Q1 dash, flows through and goes to the plate Z. Sure. So on the plate Z, it has gained charge. It had Q3 before, and now it will have Q3 and the charge coming from the plate X. Fine. Let's see. The total charge on Z will be Q3 plus the charge which has come from Z, that is Q1 minus Q1 dash. Our purpose now in this problem is to know what is Q1 dash. What is the value of Q1 dash now? What to do? I have to think of a constraint. I have to think of a condition in order to find Q1 dash, and the beautiful condition that we have is that once plate X is connected to plate Y through a conducting wire, the two plates are at the same potential. So Vx equal to Vz when the switch is closed. Well, so find Q1 dash, we will use the condition Vx equal to Vz, because both of them will now be at the same potential. Fine. I find Vx, I find Vz, and I equate the two. And in order to find Vx as well as to find Vz, I use the standard SPP, the superposition principle. Alright, let's go on. So the potential on X, kq1 dash upon R1 due to itself, plus kq2 upon R2 plus kq2 upon R2 due to the plate Y, and the contribution from the plate Z, that is kq3 by R3 plus kq1 by R3 minus kq1 dash by R3. This is Vx. Now let's talk about Vz. Potential of Z is due to plate X, due to plate Y, and due to plate Z itself. So here you are. kq1 dash by R3, it's an outer point for the plate X. kq2 by R3, once again an outer point for the plate Y, and for the Z, k upon R3, and the total charge on Z, Q3 plus Q1 minus Q1 dash. Now the job is done actually. So just do a little bit of cancellation, same thing, cancel this and that, and a little bit of simple mathematical adjustment. I get Q1 dash into 1 by R1 minus 1 by R3 is Q2 into 1 by R3 minus 1 by R2. Okay, so Q1 dash is Q2 into 1 by R2 into R2 minus R3 upon R3 minus R1. Just have a close look at this expression of Q1 dash. There is something very interesting you are going to remark. Q1 dash has, okay, R1 by R2, forget it. R2 minus R3 in the numerator. R2 is less than R3. So overall Q1 dash will be negative, and it will be a negative fraction of Q2. Q2 is the charge on the plate Y. Plate Y remains floating when S was open and when S is closed. So the total charge on plate Y remains conserved, that is Q2. So the charge when the switch is closed, the charge on the plate X is a negative fraction of Q2. Very interesting. And then of course the charge on the plate Z increases by that same amount, because whatever charge is now, whatever is the charge on X, the remaining charge has gone on the plate Y, or plate Z, I'm sorry, it's gone on the plate Z. So this is what we have done, the charge distribution after the switch is closed. Surely I can now build up further to this many things. I can do many things. Potential at a certain point, potential of the plate Y, energy of the system, and so on and so on and so on. I've done those kind of things in some of my earlier videos, and with this I wanted to explain to you a certain aspect. When the plate X is joined to the plate Z by a conducting wire passing through the plate Y, then what happens? What happens to the final charge distribution? I hope you have enjoyed the video. I really thank you for watching.
If you like the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.